Spray Drying. Today's speakers of our webinar are Dr. Jenny Weissbrodt from Symrise and Audrey Maudhuit from Fluid Air, and I will introduce them in more detail later on. The least important person in this webinar is me. My name is Stephan Druch. I'm head of the Food Technology and Food Material Science Department at the Technical University of Berlin, and I will guide you through the webinar today. At first, some technical details. During the webinar, your microphone will be muted. Please ask your questions through the questions and answers window of our web tool and use the chat in case of technical questions. The webinar will be recorded and will be made available as an on-demand video at the website of the Bioencapsulation Research Group. This brings us to the next major point. The webinar is organized by the Bioencapsulation Research Group. If you are not part of the association, I strongly recommend to join the family. I have been adopted in 2008 as a young scientist, and being active in the BRG allowed me to build up a strong scientific network in a very familiar environment. As you can see from the data on the left-hand side of the slide, BRG is really a worldwide network of scientists from academia and from industry with multiple activities providing support to your R&D projects. Co-organizers on the right-hand side are the partners and participants of a European project, a Horizon 2020 project called NCAP for Health, a project that focuses on innovative materials and technologies to improve functionality of delivery systems for functional food ingredients. Let me now introduce our first speaker. Dr. Jenny Weissbrodt is with the BRG for even a much longer time than me, so probably since the beginning of the 2000s. Her life is dedicated to encapsulation technologies, as you can see on the right-hand side. She holds a PhD in food technology from the University of Bonn and works on spray drying for more than 20 years. For 10 years now, she is with Symrise, where she is leading the technology scouting and development group within the flavor division. Focus technologies, as you can see on the bottom of the presentation, comprise all major techniques for encapsulation, and therefore I look forward to Jenny's presentation on spray drying.
Hello and welcome everybody to my short introduction into encapsulation by spray drying, including a case study I did at my department with a master's student concerning improvement on volatile retention by using phase diagrams. So at first, a very short overview how our way will go the next minutes. I will give you an introduction into encapsulation methods in the food and flavor industry, just a very few seconds on it, then go deep into the spray drying factors, how you can influence your outcome of your spray drying process. Then I go to my case study, the formula development based on ternary phase diagrams, and try to transfer this to a real system and come to a short conclusion. So which are the main technologies used for encapsulation in the food and flavor industry? The most probably used technique is spray drying because it's an available technology. You can do it with the highest throughput. You can get fairly good results. You transform your active into a dry powder, which can be easily applied in the secondary processes. The next one would be extrusion, normally the hot melt extrusion, which leads to a kind of a glassy inclusion of your active with a very nice shelf life. This is why this technology is very often used. And we have a lot of fluidized bed technologies, agglomeration processes, granulation, coatings, which are even very often used. And then just a few application fields use compacting, chilling, or molecular inclusion processes. Concerning the or shell capsules, we have submerged or free nozzle extrusion processes, drip casting processes at least, and complex cultivation. But there are just a few applications in the field of food and flavor industries. So let's come to the spray drying. Spray drying, from the first view, it's just a very simple process. It's just liquid in, powder out. Obviously, you can do a lot of mistakes during this processing. The first thing you should do is to just prepare a proper emulsion or suspension of your active in your carrier material. Then this liquid is more or less atomized into the drying chamber, where it comes in contact with circulating hot air. The particles dry and can be harvested at the bottom of the spray drying tower as a dry powder. You see you have your active, in this case, it's a flavor included in a matrix of your carrier material. This process is very useful even for heat-sensitive materials, because the temperature the particle really gets is always below 100 degrees C, and this is because the particles are cooled by the evaporation of water. This is a very energy-consuming process, and this is why the temperature never exceeds 100 degrees C. Only you are in the range of 80 to 90 degrees C. So out of this process, you get small, comparatively small particles of, let's say in lab scale, 10 microns, up to 100 microns in an industrial scale. To make particles bigger, a new process step has been introduced several years ago, and this is the fluidized bed spray drying. This means that a fluidized bed is introduced into the drying chamber at the bottom of the drying chamber, so that the particles are not directly harvested after they have dried, they are recirculated partly. The particles are more or less fed by the fluidized bed to a sifter system, where the fines are separated from the coarse material. The coarse material is what you get out as agglomerated powder. The fines are recirculated back to the very top of the spray drying tower. They come in contact with a nebulized slurry here. This is where the particles get partly wetted on the surface, and then on their way down during their drying in the drying chamber, they come into contact and stick together because of this partly wetted, sticky surface. They will have dry and can be harvested as a final agglomerate particles. These particles have a very loose structure, and this is what is really aimed at this process, because these loose agglomerate have an instant solubility. So if you put these particles or these powders into a liquid, the particles will directly sink to the very bottom of your glass and then dissolve very easily. The particles here are around 100 to 400 microns. A flavor load in any kind of spraying process typically is 20%. Of course, it can go from 2 to up to 50% load. We have no dusting in this process. This is why this process is used for many application fields where dust in the process, in the secondary processes, have to be avoided. So it sounds quite easy, this whole spray drying process. Just put a liquid in and hope that you get your active in a high amount out. But you can really influence your outcome of this process very much by a proper setting at first of the emulsion properties. Of course, the technical part even plays a role, but normally if you start with spray drying, you have to deal with the equipment you have. You don't have the possibility to change a lot. And this is why I will concentrate in this session on the emulsion properties, the things you can really change to get the best results out of your drying process. So here you have to look, and we will do this in this session, on the core and capsule properties, on the ratio of core to shell or active to material, on the emulsion size, which means the distribution of your active in your carrier matrix, then possible capsule material interactions and interactions of core and shell. All this will directly influence your drying behavior of the particles, of course, the retention, but even the particle morphology and at least the shelf life stability of your final product. So to make it easy to get an overview of what happens within a spray drying process, I will work with some models. The first thing concerning your core material, you have to ask, which kind of core material do we have? Is it a simple substance, or is it a mixture, a more complex core material? What about the molecular weight? Because this directly influences the diffusivity of your component within the matrix, during the drying, but even afterwards during the shelf life of your product. Then the vapor pressure, of course, because drying processes use heat. And of course, the vapor pressure of your component plays an important role concerning the retention. Then the in-feed concentration, how much will you load your particle with your active? And then the solubility in water, because the mechanism of transportation of your active within the drying droplet is very much dependent on if it's water soluble or not. Then the shell material. Is it a simple component, or do you use a mixture? Of course, if you need, for example, some surface activity or emulsifying properties, you might use a little bit of a more expensive emulsifier and then add some bulk material just to make the drying process itself more economic. What about the molecular weight of your shell material? Because this will determine the film density of the drying droplet directly at the surface, and this determines how much of your volatiles, for example, will be lost during the evaporation of water. Then the solubility, of course. You need a high solubility at low viscosity, because then you dry less water as possible in your process, which makes it more economic. Of course, the surface activity and emulsifying properties are not just used or just necessary for emulsifying your active if it's not water soluble, but it has even an influence on the drying droplet, because surface activity or a surface active component makes your surface a little bit elastic. And this can be useful in the drying of the droplet, because it will just prevent to a certain burst of your particles. Coming to the core material, what did I choose for this talk? I'd chosen ethanol as a water-soluble volatile material, very easy to determine, and you can imagine it's difficult to keep inside this capsule or this drying droplet, because the molecular size is quite near to water. So if you can keep ethanol in, it would be even easier with most of the other water-soluble volatile components. And an orange oil, this is a water-insoluble component, non-volatile, very sensitive, for example, to oxidation, and this is why it's used very much in the literature. As shell material, I choose a modified starch, an OSA starch, which is very surface active, a very good emulsifying material. It has a medium molecular size and therefore a moderate viscosity, which means I can take comparatively high contents in my mixtures. And the dextrin. The dextrin has no surface activity at all. It's a small molecule, highly branched, and therefore even at high solid content, I will have very low viscosities. So let's look what happens if I encapsulate with my ethanol in these carrier materials. I just would show pure materials in this case. As a response factor, I chose a retention of my actives in the matrix. As variables here, I have the solid content with Tm and the outlet air temperature with Ta. What you can see for the starch is that there is not a really high impact on solid content and outlet air temperature on the retention of our ethanol. It's comparatively, you just have to believe it, comparative good retention under these conditions. But there is not a big change with my variables. But at the end, a high solid content and a high outlet air temperature, which means a fast drying, gives the best results. For the dextrin, it's obvious that only the solid content can save your life. So just put in as much you can of your carrier material. If you don't have a dense surface film, and this dextrin is not surface active, it will not build a surface film on the drying droplet. Just to keep your ethanol inside during your drying process. Just a high solid content will help in this case. The same materials for the encapsulation of orange oil. You will see here in the first picture that whenever you have a good emulsion, all the other factors are not really important for a water insoluble component. Whether you use a low solid content or a high solid content, whether you dry with a moderate outlet air temperature or a high outlet air temperature, it doesn't make any difference at all. For the dextrin, here you have to dry fast. Yes, it's true. Just put in as much solids as you can. But in this case, you see an opposite effect concerning the outlet air temperature. The outlet air temperature, an increase in outlet air temperature leads to a drop in the retention. So what is happening here? The outlet air temperature determines the temperature of the droplet itself, it's drying. And this means the higher the temperature, the higher the kinetic energy. And this means that the movement, the whole, the turbulence within your droplets will be higher if you have higher temperatures. And this means that constantly your active is transported to the surface and will get lost if you have a higher temperature. And this effect can be seen here. Coming to the core to shell ratio and the solid content. Normally in spray drying, you have very often this ratio of 1 part active to 4 parts of solids or carrier material. Of course, you can change this relation however you need it, but you have to bear in mind that a higher core content or active content normally leads to a lower retention because you just have less material to unwrap, to entrap it. A very high solid content leads to a very fast formation of a crust or of a membrane on the surface of your drying droplet, and this will reduce losses of your volatiles. But on the same side, your solid concentration affects the viscosity of the drying droplet. If it's not too high, it will prevent too high internal mixing and movement within your droplet, and it will keep your volatiles inside. If it is very high, it will just increase your drying time, and this can, in this case, lead to a higher loss of your components, and it will directly influence the particle structure. Let's have a look at our orange oil in our starch and dextrin matrix. On one axis, I present here the ratio of core to wall material. 3 means 1 part active, 3 parts wall material, up to 1 part active, 6 parts wall material. You see, of course, the retention increases if you increase this ratio. The more material you have to entrap your active, the higher will be retention. The solid content, we've seen it before, doesn't have an influence at all. For the dextrin, of course, the solid content is important. Even here, it is important. And the ratio of your active to wall material too, which means just have as much material as possible to entrap your material and then have a high solid content. And then you have a chance to have a fairly good result, even for this not emulsifying carrier material. Let's go for the emulsion size. Emulsion size in this case means the distribution of your active within your matrix. Of course, for water-soluble volatiles, it doesn't make any difference. You put it in, it will completely mix up with your continuous phase with your water. You don't need to homogenize or something like that. The emulsion size is not important because it's not there, at least. In this case, just a fast crust formation during the drying process is important. For water-insoluble volatiles, you need a homogeneous and fine emulsion because this will give you a high stability during processing. This means that the first few milliliters you spray dry will have the same quality as the last milliliters you spray dry. So you prevent a demixing, a coalescence, a breaking up of your emulsion during the processing. Thereby, it will increase the retention because of this nice and fine distribution of your active within the matrix, and it will even decrease the surface oil. You can see this here for the orange oil. We have, again, the solid content from 20 to 40%, and the homogenization time. We just used time here to have a continuous factor. It means 0 homogenization 5 minutes, which is 1 pass at 200 bar, and 10 minutes means 2 passes at 200 bar homogenization pressure. You see, the finer your emulsion, the better is your retention for our orange oil within the nice emulsifying material. For our non-emulsifying material, the homogenization is even more important, because here you don't have this film building which the starch will do on the surface of your oil droplet. You just have the chance to distribute your active as fine as possible within your continuous phase to have any kind of retention. And this is, of course, supported by the solid content, because a higher solid content means you have a high viscosity, and this will stabilize your emulsion too. Coming to the feed viscosity. The feed viscosity directly affects the retention, the drying time, and the particle morphology. If you have a very low viscosity, you have a very high degree of internal mixing. The movement within your drying droplet is very active. Yeah, the kinetic energy is high as the particle heats up, and the molecules are just moving around. And even the oil droplet is moving around a lot, and this means during time of drying, the oil droplets are transported to a greater extent to the surface of your particle, where your active can be lost. If you have a moderate viscosity, you drop down this internal mixing to a certain extent. You get larger particles out of your drying process, have a reduced surface area, which is very favorable for your shelf life. A very high viscosity can reduce the drying rate, which means you just drop this internal mixing to an extent that the water transport to the surface of the particle is reduced too. And this means that the drying rate will drop. And this means that possibly you have a crust formation, the surface densifies, it dries, and then there is still some water remaining within your particle. Now this water goes up into it evaporates. You have a water vapor bubble within your particle, and this can cause a particle bursting if this water is not able to move out of the particle. An example here for the spray dried ethanol. We have again the outlet air temperature in this case and the solid content. What we can see for the starch is a high solid content and a high outlet air temperature. Fast drying is a good idea for our ethanol. This means that we didn't exceed the optimum viscosity in this case. So we are still in the optimum region. We don't have a particle burst or something like this. For the dextrin, again, you can see we don't exceed the optimum viscosity. We have a fast drying at a high solid content, and this will lead, in this case, at the possible highest viscosity we've used for this design of experiment, the best results. Let's just go to the drying parameters. At first, at the atomization. Normally, spray drying nozzles offer a greater flexibility because they are not so sensitive to viscosities. On the other hand side, centrifugal wheels are more sensitive to higher viscosities, but they tolerate a certain extent or a certain size of particles within, where you can have some problems if it comes to spray nozzles. The inlet air temperature and the moisture. If you have a very high inlet air temperature and a low moisture, you have possibly a very fast drying. But if your temperature is too high, you have a drying on the surface of the droplet, it tightens up, it gets very dense, the water can't come out, and this leads to a rupture of the particles. The outlet air temperature, as mentioned, the temperature the particle itself will get. If it's too high, you can have a heat damage if you have very heat sensitive materials. And at least the residence time at the dryer, this means if you don't have a cooling system at the end of the powder recovery, You should remove your powder from time to time, especially when you're working with, for example, probiotics, because the residence time at the dryer can be very important here for the survival of your bacteria. Let's have a look at the starch. It's a very nice emulsifying property material. It makes perfect emulsions with our spray dryer, with orange oil, and whatever I do with the temperatures, inlet air temperature, outlet air temperature, we will have almost the same result. It just depends more on the homogenization process. For the dextrin, we can see that the outlet air temperature should not be too high. Here again, we have this effect of internal mixing. It should be moderate, so that you don't lose too much of your orange oil. The inlet air temperature, whether it's 190 degrees C or 170 degrees C, doesn't make a difference at all. And now you can see what happens if your viscosity is too high, or if you use too much solids and dry too fast. You see here that you have very thin shells of the capsules here. So what has happened? It was a very high viscosity. The capsule surface, or the droplet surface, dried, densified, and the water wasn't able to move out. And then it happens what I said before. The water vapor develops in the center of the particle. It didn't came out, and then it led to a particle burst. And then you see this here, it's a disaster area. Same for very high solids. If you have very high solid content, it can happen that you have a very thick shell very early in the drying process. And then again, your water cannot move out. It wants to come out, it doesn't find a way out. And then you see here, this was a water vapor bubble inside the particle which developed, it wasn't able to move out. And then it led to this destroyed particle. And what you ever might hear in your ear, it doesn't work because the weather wasn't nice enough. And if you think it's a joke, no, it's true. And I can demonstrate this to you. I was just looking out of the window and just looking at my thermometer and found out, yeah, actually we have around about 4 degrees C, 50% relative humidity. It's not the nicest weather actually. I was thinking of my colleagues in Singapore, which will have at this time 30 degrees C, but 90% relative humidity. But now what has this to do with the drying? We do drying experiments at the same time under these very differing conditions. Would this have an impact? It will, and I will show you this in a few seconds. This can be even the same question in summer or winter. If you take Holzminden for the typical winter condition and Singapore for the typical summer condition, you will see that you will have very different results just because of the weather. If we take these conditions of Holzminden and Singapore and look at the water in the air we use for drying, we can find out that our actual air in Holzminden will have around about 2.5 gram water per kilogram air. At the same time in Singapore, we'll have 25 gram water per kilogram air. So you might get an idea that the water uptake of our drying air in Holzminden and in Singapore might be different. This can be demonstrated by a Maudhuit diagram. A Maudhuit diagram gives you an overview of temperature and absolute moisture of the drying air. Here we have the relative moisture of your drying air, and you can calculate what happens in your drying process. I put in this diagram a curve for the drying process in Holzminden in red, in Singapore in green lines, and what I even put in here is a stickiness curve. A stickiness curve can be determined for any component to be dried. You measure the behavior of your powder under different conditions of humidity and temperature, and then find out when your particles start to lump, when you don't free-flowing powder anymore, where the lumping and the stickiness of your powder starts. So let's have our drying experiment with the conditions I mentioned before. So 5 degrees C, moderate relative humidity in Holzminden. What means drying? Drying means that we at first have to heat up our drying air. So in this example, I used 190 degrees C for our drying air. And what happens now during drying is that your drying air will give its energy to your liquid droplet to evaporate the water from the surface, and on the same side will take up water from this surface and transport it away. This means that your drying air will cool down and get more moist over the drying process. And this is what this line here represents. I stopped my virtual drying process at 90 degrees C outlet air temperature, and you see that a lot of water has been taken up by the drying air. We end up at round about 42 gram water per kilogram air at the end of our process here. We do the same in Singapore. In Singapore, we had 30 degrees C and a high humidity of relative humidity of 90%. So this is our starting point here. We heat up the air in the same way to 190 degrees C. You see, we are now have moved just by heating up the air. In this case, we are just very much more on the right-hand side of the diagram, which means our whole system is more moist, just right from the beginning. Now I start my drying experiment. In Singapore, the water will evaporate, the drying air takes it up, and it touches the stickiness curve. So for the same drying experiment under the same conditions in Holzminden, we will get out a nice free-flowing powder, and in Singapore, it will not come out, it will stick to the walls of the drying chamber. So what is a normal reaction any operator will do? It doesn't dry. I will increase the inlet air temperature. So what happens if we now increase the inlet air temperature? Your drying air is still the same. It has the same moisture content. So even if you heat it up, it still has the same moisture content. And if you now have your drying, you just end up on the right-hand side of your stickiness curve, which you don't have any drying. Yeah, you have a plastic mass within your drying chamber, and you have to clean up. So maybe this is the wrong direction. Let's decrease the inlet air temperature. So it doesn't dry, and what you have to do is decrease the inlet air temperature. Okay, we heat it up at this time to a temperature of 170 degrees C. And then we make our drying up to the outlet air temperature of 90 degrees C. And you see, you stay at the left side of the stickiness curve. You will have a free-flowing and dry powder. Of course, you have to drop your in-feed concentration a lot. Yeah, which means your drying is a little bit slower. It will take 1 or 2 hours longer, but on the other hand side, you don't have to clean up, and you have a constantly of your powder, and it will come out as a powder and not as a plastic mass. So you've seen that the temperature, or at least the weather, plays an important role in your drying experiments. So coming back to the spray drying itself, it's a very easy, continuous process. It's available technology you have to deal with for your special drying problem. It's very cost efficient and fast. We get a powder if you do everything. And we have almost 100% release because our powders will dissolve in water. But as a disadvantage, it's a matrix inclusion. So it's very difficult to control the release. We have temperatures above 60 degrees C, which for some substances might be an issue. And to make a really good process, you need to optimize for every active or for every group of active with almost the same properties. But if you know this and you know which are the buttons to press to get a better result, you can have a very good product. And to get an even better water product, I will present now the case study, which a master student at my department did, because I had a funny hypothesis. I said, how can we even increase or increase the retention of our volatiles which are water soluble? So there was a hypothesis. I said, okay, what happens during drying? You always reach a point where your carrier material is no longer soluble within your solvents. And what happens at this point, we are not quite sure, but it's possible that it precipitates spontaneously and includes your active. And to find out if this will really happen, we established phase diagrams, ternary phase diagrams, which represent mixtures of water, carrier, and an alcohol. With titration curves, we created different mixtures of water and carrier, and then we make a titration with ethanol in the first point. And just by measuring the turbidity, we found the point where our carrier starts to precipitate. Doing this, we could establish binodal curves for our system, which divides this whole diagram in a homogeneous and an inhomogeneous region. And this curve is the thing which was very interesting for us. So these are the curves we established for water, a maltodextrin with a low DE value, a maltodextrin and a high DE value, and ethanol. And we even did the same task with, for example, propanol and other alcohols, completely water soluble. It worked out. We found out that there are nice binodal curves which we could establish with this method just by turbidity measurement. But normally our spray drying is done not with just maltodextrin, it's done with a mixture of gamma-arabic as an emulsifier and maltodextrin. So the next question was, could we establish these diagrams with a mixture of gamma-arabic and maltodextrin if we just treat this mixture as one substance within our mixing diagram? And it was possible. We could establish even binodal curves in this diagram with a mixed carrier system. And now the question was, if we come near from the homogeneous region, near to the binodal curve, will our encapsulation efficiency be improved? And this is what we did. We kept the solid content in the first diagram. We kept it constant. We increased the ethanol concentration, and what we found out is that the encapsulation efficiency will go up too. Does it work in the other direction too if we keep the ethanol concentration constant and then just increase the solid content? We did this too, and even here we could observe that the encapsulation efficiency was improved. Now was the question, could we transfer this idea to a real flavor system? We selected a coffee flavor, which is mainly based on water-soluble components, and tried to establish a binodal curve for this flavor in a carrier system too, and it was possible. The main component, one of the main components of this coffee flavor is propanol. Here's a propanol curve. The coffee flavor curve looks completely different, but it was possible to establish this binodal curve. And now we are just testing out points on this binodal curve, because the idea was, if we know that increased solid will improve the encapsulation efficiency. Does it even work when I just walk around the binodal curve? We did this for maltodextrin. We increased the solid, still just wandering around at the binodal curve. What we found out for point 1 and point 2 is if we increase the solid content, the encapsulation efficiency for our flavor components summed up are remarkably increasing. You see here the encapsulation efficiency for any other component than ethanol higher. And this is why the results here are even much higher than for the pure ethanol system. Now we thought, okay, maybe some of the components in our coffee flavor are not completely water soluble. Maybe it's a good idea to make the same experiments with a mixture of gamma-arabic and maltodextrin, even on a binodal curve. So a phase diagram and a binodal curve could be established for the coffee flavor and gamma-arabic maltodextrin mixture. And if we are moving on this binodal curve with our mixed system, we had a almost 100% retention of our flavor. So it perfectly works even for a complex flavor. So what can we conclude out of this case study? There are phase separation phenomena in spray drying. Surprise, surprise, no one has even published anything of this before. And the knowledge of this phase behavior of our carrier in our water alcohol mixture or flavor mixture can lead to a remarkable improvement of our encapsulation efficiency. And more encapsulation efficiency means that we reduce the losses, we have a more sustainable processing, and we have an improved product quality. And this was true and could be proven even if we are applying very, very strong simplifications to make this system run. And we are so glad that this really works out in a very efficient way that we filed a patent for this type of encapsulation. I thank you very much for your attention.
Okay, thank you very much. Thanks for unraveling the secrets of flavor and aroma encapsulation. And I think we all learned now that sometimes it is good to be in Holzminden, sometimes maybe Singapore is more favorable, and we need to make sure that we exactly know where we are. Okay, there are no questions at the moment in the chat as far as I can see, so feel free to post your questions and we will proceed now with the second presentation and then finally jump into the discussion. So our second presentation is given by Audrey. Audrey is also very active in encapsulation. As you can see, she did her PhD at the University of Nantes and obviously came into contact with microencapsulation during her postdoc period at ONIRIS. She has several years of experience in the industry at a company called Phytosynthese. She was co-founder of a company which is probably familiar to some of you, Encap Process, and since 2018 she's a process engineer at Fluid Air with a responsibility for trial laboratory on electrostatic spray drying, and that is also the topic of her presentation.
Good afternoon, everybody. Thanks to Denis and Stephan to give us the opportunity to present you a really innovative technology. It's an electrostatic spray dryer that we use for thermosensitive compound and other applications that I will show you in this presentation. My name, so it's Audrey Maudhuit, and now it's 3 years ago that I work with this nice technology. Before to present you far away this technology, a short word about Fluid Air. Fluid Air, it's a solid dosage equipment. We have a fluid ice bed, Asha granulation, milling, and it was created in 1983 in US, and we are a division of Spraying System. Spraying System, we have many offices around the world. So today I will give you a short word about Polar Dry, how it works and what is the advantage to use Polar Dry. I decided to show you, we have many scientific evidence, and I decided to show you one with microalgae application. And to finalize, it's just to give you some detail about what we can do. We have a laboratory in Europe, in Nantes, close to Denis, and we are really welcome to do some trials on the laboratory model. So about Polar Dry, so what is the challenges that Fluid Air identify now, 5, 6 years? We know that in the market, we have two main drying technology. The first one is the freeze drying. It's nice when you have thermosensitive compound. You can work at low temperature. You obtain a really high heat, but unfortunately, when you finish your process, it's a batch process, and when you finish your process, you obtain plates that you have to squash and after to mill to obtain the final powder, and moreover, it's really an energetic consuming. On another hand, if you want to go really fast, you have the conventional spray dryer. It's a continuous process. You have really large equipment, for example, for milk to have milk powder in Australia. But unfortunately, you have to work at really high temperature, around 200 degrees C. And moreover, the particle size that you obtain are really small for us, between 5-10 micron. So Frida decided to combine advantage of both of this technology. That means to work at lower temperatures than the conventional spray dryer. When we say lower temperature, we say between 35 to 60 degrees C to obtain a high yield when we use a sensitive compound, sensitive active, working continuously, and also to assure to have a large-scale equipment. That means that today we have laboratory equipment, but also industrial equipment. If we talk a little bit more about advantage, the first one, but not the least, it's to work at lower temperature. How it's possible? When we work with a conventional spray dryer, we know that we have two periods. The first one, it's a constant wet period, and during this time, you don't need to apply a really high temperature to evaporate water. The water is at the surface. But after, during the drying, after a longer time, you go to the filling when period. That means that you have the creation of the crunchy shell at the surface, and you still have water in the middle. So you have to apply a really high energy, and in this case, temperature, to finish to evaporate the water in the middle. In case of polar dry that we do, we apply an electrostatic charge in the solution. When we do that, we help the water to move really faster to the surface. That means that we increase the diffusion rate of the water. And like that, you don't have to apply high energy to remove the water, stay in the middle. And moreover, you create a thin layer of water of other solvent, polar solvent that you can use, and like that you have a really high protection all during the drying of your compound. So that means that the only temperature that see your compound is the outlet temperature. When we do trials, we always be careful on the outlet temperature and not really on the inlet temperature. The fact that we apply an electrostatic charge, we change also the particles that we obtain. We change the surface, and moreover, we can play with the electrostatic charge to have low and high electrostatic charge. That means to have little bit sticky particle and not really sticky particle, and like that you can agglomerate together, and we can reach a particle size around 250 micron, and in special case 500 micron. So it's really interesting if you want also to agglomerate. Moreover, the fact to agglomerate, to change a surface less porous, we can also increase the flowability of the powders that you can have. We increase also the hydration wettability of your powder. This system works with nitrogen. That means that all compounds we can avoid to have an oxidation. I will show you some more detail with microalgae application. And I say you that we apply an electrostatic charge. It helps the water, so a polar solvent, to move really faster to the surface, but it also means that it's play on the compound with different polarity. So in function of your polarity, you can also stratify your compound inside. For example, when you use oil, vegetable oil, the oil, it's no polar, stay in the middle, and you have a carrier, for example, modified starch, and the modified, you have a perfect encapsulation with the modified starch, and you can go up to 50–70% of oil without at the surface. So it's really powerful. So to give you a little bit more detail about scientific evidence that we can do, we have 6 laboratories around the world where we do case of study, and we are also support for consumer. So we have different kind and different study in different laboratory. The first one, it's an inhalation application. We have also microorganism application. The fact that we work at really low temperature, it's really help to have a good viability of bacteria. For example, we work to work directly to the direct compression, which changes the flowability and the structure of the powder. So it's possible to go directly to the compression. We have also applications that I say you on oil and other, for example, DHA oil, essential oil. My colleague in Australia work a lot on lactoferrin and colostrum, microalgae that I will show you. We have also application on natural resin, probiotics, close to bacteria, vitamins, and other, and we discover every week a new application. That is really great with this new technology. So I give you short detail about microalgae. This study was done with the University of Nantes. They give us microalgae, they concentrate at 12%, and we decide to dry it at 90 degrees C at the same time with a conventional spray dryer, a bulky one, and an electrostatic spray dryer, it's with polar dry. So the first result that I show you is we wanted to check the water activity with a target below 0.3. And that you can see with an electrostatic spray dryer, it was possible to obtain this target to compare with a conventional spray dryer. That you can see here. So I say you that we work at 90 degrees C of inlet temperature, but we change a little bit the flow rate and the gas inlet. So that means that we need 30% less energy working with the electrostatic spray dryer to the conventional spray dryer. Even if we decrease the energy needed to dry, we obtain lower water activity. So it's really great information. Moreover, after we check the pigment gain, that means the more pigment that we have to compare with a conventional spray dryer, and that you can see with the chlorophyll R and the carotenoid, we increase by 30% the quantity of pigment. And in case of chlorophyll C, we increase by 150%. So we really avoid to have denaturation and degradation. And we know moreover that we have this result because we work with nitrogen. So it's the powder that you obtain. So you can see we have a wettability that you can see on the right. And also we did some SEM pictures. The first things that you can observe is we can increase the particle size. That I say it was possible to agglomerate particles, and in this study we increased by between 2 and 3. Moreover, we also observe that we have a really different shape to compare between the polar dry air and the spray dryer. So that means that we develop a new functionality, and we continue to work with university to understand what's happened. Just to conclude really shortly, so you have an electrostatic effect that we apply in the solution. When you do that, you don't need to apply a really high energy, high temperature to finalize your drying. So we work at lower temperature. The fact to to play on the polarity of the compound, we can stratify each compound inside your particles. Moreover, we can also agglomerate, that I show you. It's a full product line. That means that we have the laboratory scale and we go up to the industrial scale, and you can change really your powder characteristic. You increase your viability, you avoid denaturation, you increase your flowability, your wettability, and you can also play on the particle size. Thank you so much for your attention. Feel free if you have any questions. Thank you so much. Good afternoon.
Okay. Audrey, thank you for that comprehensive overview. And I'm really jealous that we are discovering new applications every week. That is an exciting, obviously an exciting topic you are working on. So we have some questions in the chat, and I think some of them have already been answered by Jenny. And I think there are two more are open. The first of one was Jenny, if you have any idea on how to compare the behavior of modified starch and gamma arabic or maltodextrins with different DE.
This would take a day to make it to make it really concrete. Modified starch are standardized substances which always have a very nice and always the same emulsifying properties and even the drying properties. Gamma arabic is a natural product which will change a lot during the seasons and maybe even from one supplier to the other. Maltodextrins can be divided by their DE value. If you have a high DE value, you have smaller molecules, less viscosity, but a higher hygroscopicity. A low DE value means you have a bigger molecule, less hygroscopicity, but a higher viscosity. This is very short version.
Okay. And a second one was referring to the consumer desire for clean label products and clean label materials for encapsulation. What your favorites?
What can be more clean than maltodextrin? It's food. Maltodextrin is food. I know we have these issues within the company too. Normally, gamma arabic is a very natural substance. Okay, I understand some issues with a modified starch because this has an E number and can be claimed in any other way. So then maybe gamma arabic would be a nice idea. The maltodextrins can be claimed as maltodextrins. You can even try to use, for example, starches, native starches, or flours as carrier systems, but they don't work that properly as maltodextrins do because they are designed for spray drying. So it's very difficult to find an appropriate substitute for maltodextrins.
Okay. Then I have also took down some notes for questions for Audrey. One question was simply the throughput of your polar dryer.
It's really depending on the solid content that you apply and the inlet temperature. So it's really difficult. We start with the model 0.1, mean 100 milligram of evaporation of water maximum, and we go up to 100 kilogram per hour of water evaporation in maximum condition. And after, it's really depending of the inlet temperature and also of the solid content that we spray, of the solid solution that we spray.
Okay. Another question was on the advantages of the polar dryer compared to gas pressurized assisted electro-spraying.
If I remember well, when we use the second technology, it's not the throughput, it's not so good, it's only a laboratory scale. And today we have a molar scale, but we just started a PhD on this study just to compare really well what's happened. The charge is not exactly applied at the same way, so we want to understand a little bit more where exactly the advantage of both.
Okay, and the second one on the particle physical properties of your product, how the polar dry affects the molecular packing or free volume of the carrier materials?
I think it's more on the phenol product. That's it, on the density of the phenol product. It really depends that we want to have. You can apply a continuous electrostatic charge, and in this case, you will increase the density of the single particles. In case of you want to have agglomeration, you will create a little bit lower density. But yeah, after it doesn't have a high impact. We continue to have a really great flowability and hydration.
Okay. Well, then we stay with the questions concerning your presentation. We have one more. If polar dry allows to spray at higher solids compared to conventional spray drying.
We have to compare. Today we go to, it's really depending on the viscosity. That's a Jenny said, it's really the main important parameters that we have. Today it's really depending on that. We say that we can do a little bit more higher solid content due to the fact that apply an electrostatic charge will help to don't stick too much on the nozzle and help to reduce the surface tension. And we also use a bifluid nozzle, so it's easily to work with a high viscous solution. Okay.
Jumping back to Jenny, what is the best maltodextrin dextrose equivalent in spray drying, to your experience?
It depends.
If it, my students answer in the exam.
It's a good answer. If it comes to protection against oxidation, a high DE value might be favorable. For example, if you need to capture more volatiles, maybe a bigger molecule would do, then a lower DE value might be a better idea. So it's quite difficult to decide, and you still have this issue of hygroscopicity with the high DE values. So you have to balance it a little bit. It's not so easy to answer this question.
Okay, and then I have a next one, which is for me really a tough one. If you have a product that is insoluble in a polar solvent, someone is looking for a solvent which is acceptable in spray drying. So it is possible to do it with halogenated solvents, but the person is looking for something more sustainable.
Why don't you prepare an emulsion? This is why an emulsion is prepared in spray drying, because your active is not soluble in water. Then you have to add an emulsifier like gamma-arabic or a modified starch. Prepare an emulsion with your emulsifier and a carrier, for example, in maltodextrin, and then you just have solved this issue of non-solubility in water.
Okay. So this is all the questions I can see in the chat. There is one more, suggestions for carrier for dairy applications. This is probably also quite a wide field, but maybe you can comment.
Yeah, in former publications, you will find some publications where, for example, milk proteins are used as emulsifier and lactose as carriers. So if you want to stay within the medium, this would work.
Okay, and there is one more on the maltodextrin. If the origin of the maltodextrin, if it is corn or wheat based, has an impact on the retention of volatiles.
No, just on the declaration if it's an allergen or not. If it's wheat, it's a EU allergen, this might be an issue, but the functionality will be almost the same.
Okay, very good. I do not see any more urgent questions. So we had a total of 153 participants in the webinar, which is again quite a really good number and shows how well this format of the BRG now is accepted. And this brings me to the point that we to do some merchandising or so doing some announcements that there will be the 23rd Microencapsulation industrial convention in 2022 in Rotterdam, organized by the BRG, that we will have the international conference on bioencapsulation in 2021. And we have some more webinars to come. The next one is on February 18th, and where we are going into more detail in the spray drying. And Jenny mentioned several times in her talk that emulsion properties are important, and she was talking about her perfect emulsions, and I will take you to the interface of the emulsions to see how emulsifier film at the interface may affect the properties of your capsules and the functionality of the product you have. It is accompanied by a presentation by Lex Nunnery from Vertellus in Belgium, who will present some innovative materials for encapsulation. And then, as you can see, we will continue in March and April on microencapsulation in foods, in pharmacy, and in microencapsulation by membrane emulsification. So it is always worth visiting the website of the BRG to see the upcoming webinars, to stay in contact with the community and some hot topics. Okay, so thank you for your attention today for the discussion, and we hope to see you again soon in our webinars. Have a nice afternoon. Bye.
Bye.
Thank you. Bye.